So obviously there's a lot of topics that we covered last semester. Again, most of it, a good bit of it, we've been just mulling over and over and over again this semester as well. But some of it maybe we need a good sort of review for. Okay, so we will do sort of practice reactions and stuff like that. Before we dive into that, I want to actually go a little bit simpler and do stuff like hybridization, right? We can even go like first semester business here. Oh, not CH3, CH4. So I'm just going to draw some molecules. I'm going to indicate a few of these atoms. And you are going to tell me what the hybridization is. First of all, when I say hybridization, what kind of answers am I talking about here?
Like sp2.
Yeah, sp2, sp3, sp, all that good stuff, right? Oops. Let's actually do this. All right, so when we do hybridization, the whole logic is that there's a really simple correspondence between the number of electron regions about an atom and the hybridization of that atom, right? So electron regions, what the heck do I mean by that? That is a bond of any order or a lone pair, right? Those are what we consider to be electron regions. Okay, and there's a simple correspondence between the number and the hybridization. So if there's 2 electron regions, that's sp hybridized, 3, that's sp2, and 4, that's sp3. Okay. All right, so now we're going to take our simplest molecule, methane. right? If we're looking about that carbon, there are 1, 2, 3, 4 electron regions. So that guy is sp3 hybridized. Do you remember the geometry that corresponds to that?
Isn't it tetrahedral?
Yeah, tetrahedral, right? So that's that weird word. Awesome. Okay. So now we're going to go over here. All right. So now we have these stick structures. So I think the only thing that kind of makes this a little bit more complicated with the stick structures is, remember, not all your bonds are necessarily drawn. Right. So I can see very clearly that I have 1, 2 electron regions. Note that double bond just counts as 1 electron regions. That's that bond of any order, right? So double bond, single bond, triple bond, that's still just 1 electron region. But I also have this sort of hidden or not explicitly drawn hydrogen right here, right? So that would be a 3rd electron region. So this guy is sp2 hybridized. What is the geometry associated with sp2 hybridization?
Trigonal plane.
Trigonal planar.
Nice, yeah. Okay, and then this guy here, we'll just go quickly, right? This one actually has 3 hydrogens that weren't explicitly drawn. So 1, 2, 3, 4 electron regions. So this one's sp3 and tetrahedral. All right, what about ammonia? What's that nitrogen?
sp3.
Yeah, right. So again, this is now the lone pair also gets counted. So if I'm going to just draw my Lewis structure for ammonia, I got 1, 2, 3 hydrogens, but also this lone pair. So 1, 2, 3, 4 electron regions. What's the geometry?
Tetrahedral.
So the electron geometry is tetrahedral, right? But what's the bond geometry? Does anybody remember? We can draw our little perspective drawing here. This is what the electron geometry is, but then I got to go in and erase one of those bonds because it's really a lone pair.
That would be trigonal.
Trigonal.
Planar.
No, not planar.
Is it bipyramidal?
It's just pyramidal.
Pyramidal.
All right, so here's my little triangle-based pyramid that I got. They don't all lie in the same plane, so it's not the same geometry as a trigonal planar. They're sort of kinked out of the plane a little bit. So that's what happens when you have a lone pair, right? It essentially takes the place of one of your bonds, and so it changes the geometry slightly. And again, you can kind of visualize it by starting out with that electron geometry and then just erasing one of those. That's your lone pair. Okay. What about this guy here?
SP.
Yeah, so it's just sp right now. We have 1, 2 electron regions. And what's the geometry associated with that?
Linear.
Linear.
Yeah, so that's linear. Okay, now these 2 examples are more difficult. Okay, and that's because this concept of aromaticity comes into play. This nitrogen right here, if we were just going to use our sort of simple rules as before, we would say there are 1, 2, 3, 4 electron regions, right? Counting that lone pair. And so we'd be really tempted to say that this is sp3 hybridized. But that's not the case. What is it?
It's sp2.
It's sp2. And why is it sp2?
Because the lone pair is in the outside, so we don't count them.
No, it's not. It's actually kind of the opposite reason. It's because the lone pairs want to be in a p orbital, so this compound can be aromatic. Right? In order to be aromatic, you couldn't have an sp3 hybridized nitrogen there. That would mess everything up. All right, so this is what we saw. It was the same thing. We saw this last chapter. It was the same deal for furan, right? Furan has 2 lone pairs. One of them is in a p orbital, the other in an sp2. So this is all from last chapter. It might be a good idea to go back and look at that, but this has to do with aromaticity. If it makes the compound aromatic, as is the case here, it'll change the hybridization on that heteroatom just so that it can be aromatic. And then you have the opposite situation here. So this was probably one of the harder problems on your exam. If this nitrogen is sp2 hybridized, would this compound be aromatic or anti-aromatic or non-aromatic? If that lone pair is going to participate in that ring.
Then it would be aromatic.
So then we would have 2, 4, 6, 8 electrons in that ring.
Oh, then it would be anti-aromatic.
Anti, why is that?
Because it doesn't follow the rule.
Yeah, so right,
4n, whatever,
that
plus
4n
2.
plus 2 business going on. Now, in terms of stability, aromatic is the best. Then you got non-aromatic. And then finally anti, that's like the worst. So this is in terms of sort of most stable, least. Okay. Let me get rid of my coloring real quick. So if it puts that lone pair in a p orbital, then it's anti-aromatic. That's the least stable, right? So instead, it goes ahead and doesn't put it in a p orbital. It's sp3 hybridized. So this guy is actually non-aromatic. Okay, so those were like two of the harder problems on that last exam that most people miss. So just something to make note, right? It could be, basically that nitrogen gets to choose. If it puts its pair of electrons in a p orbital, that would be anti-aromatic. That's bad. If it keeps it in an sp3 orbital, that's non-aromatic. It's not great, it's not aromatic, but it's better than being anti. Okay. Most important thing to remember though is that 4n plus 2 rule, right? That's what makes it aromatic versus anti-aromatic. All right, crash course in hybridization. So hybridization as well as the geometry associated with it. Cool. Is there something else kind of early on like that? Oh, right. So now let's do just some review with chirality, assigning stereoisomers, RS, EZ business, okay? Because I know that this is everybody's most favorite topic that, we've had. So give me the R to butanol. Let's go E. Right, so assign stereocenters as well, so give me the structure of these two and then give me the stereochemistry of the bottom two structures.
For the second one, that 2-butane or Z?
It's a 2-butene, sorry. Okay. Yeah, my 2s and my Zs are the exact same, except for my Zs have a cross through the middle of them.
Do you want the actual structures or do you want the projections for them, if that makes sense?
Well, when you give me the structure, because the stereochemistry is indicated, you'd have to give me like the dash or the wedge bond.
Okay, that's what I wanted. Okay.
All right, let me get you attention for one second. I'm going to go through one of these examples just to kind of remind everybody of what's going on here, and thus, if you're stuck, it might help. Let's do this one first. I think it's kind of the easiest here. So first of all, there's only one stereocenter in this molecule, right? Where's that? I guess I kind of made it easy here, right? Why isn't this guy a stereocenter?
It has two CH2s bonded to it. They're the same group bonded to it.
Yeah, and it could be a little bit, right? It's the bottom line is if you sort of look on either side of this molecule, let me use a different color. If you look on either side, you know, you have your eyes and you're looking either way, this molecule would be exactly symmetrical. I could mess things up if I had a bond over here, for example. All of a sudden, then that carbon does become a stereocenter because it's not perfectly symmetric. So, Eric, you're kind of like half right? These are still both CH2s, but now that I have this guy over here, it's what messes up that sort of symmetry. Okay, so make sure to keep an eye out for that. But yeah, the number one rule is, what are we looking for? We're looking for a carbon that has 4 distinct bonds, right? 4 different bonds associated with it. So that's this guy here. All right, one thing is not drawn on this carbon, one of my bonds, right? So that's hydrogen is going to be pointed back. So this is kind of best case scenario, right? When the lowest priority group is pointed into the page. Now I just have to assign priorities. What's highest priority?
Chlorine.
Yeah, right. So highest priority means highest periodic number, right? Most protons. So then fluorine, and then the carbon, right? And since the lowest priority group is in the back, let's just sort of make little notes. That means that R is what? Clockwise or counterclockwise?
Oh, R is clockwise.
R is clockwise. And so S is counter. All right, so then we go from 1 to 2 to 3. That's going counterclockwise, right? So this would be S stereochemistry. So I want you guys to do this one on your own especially, but let's sort of move real quick. I think the R and S is a little bit tougher than the E and Z. What do we remember for E and Z?
Z same side.
Z same side, awesome. So this is, if it's E, that means that they will be on opposite sides. Okay, we could also call this, what, cis or trans?
Trans.
Trans, yeah. Okay, so now let's do the butanol. So first of all, if you're going to go from the name to the structure, the first thing to do is just figure out like kind of the shell of the structure and worry about the stereochemistry last. Right, so if this is a butanol with 2, we're talking about an OH group at position 2. Now I gotta figure out if that thing should be pointed backwards or forwards. Okay, what I'm gonna do is just sort of pick one and roll with it. The easiest thing is if my lowest priority group is pointed into the page. So I'm gonna start out with the OH group pointing out, and then I'm just gonna double check my work. Highest priority will be that OH group. Now, which one of these 2 carbons, carbon 1 or 3, is next in my priority list?
Carbon 3 is.
Yeah, carbon number 3 gets priority 2. And so this guy's 1. Oh, no, that makes no sense at all. This guy's 3. Okay, so now I go and double check. This is indeed, boom, boom. Awesome, okay. Now, what if instead I had said S? What would be the easiest thing to do in order to get this to be the other enantiomer?
Change the.
You could put the hydrogen on the wedge.
Yeah, oh, absolutely. So, and what Nebia was saying, basically, you're just going to switch this from being a wedge to a dash, right? That's the easiest way to get the mirror image of something. Cool. So now everybody take a second and do these two stereocenters here. Make sure that you know how to do it when your lowest priority group isn't pointing to the back. All right, so I'm going to focus on this one first because it's going to be the easiest. And it's going to be the easiest because my lowest priority group is already pointed to the back, right? So fluorine's 1, this guy's 2, my methylcarbon's 3. So that makes this an S stereocenter. All right, this has 2 stereocenters, so I got to jump to the other one. Now, this has the exact opposite situation. Now my lowest priority group is pointed where?
Towards us.
Towards us, right? So my lowest priority group is now a hydrogen that's on this little wedge. I'm going to get rid of that. We could sort of like rotate this molecule in our mind or something complicated like that. Or we can just flip the rules, right? So now if lowest priority is up front, R is counter, and S is clockwise. All right, that's kind of the easiest way. So here my OH is 1, this guy's 2, this guy's 3. That's counterclockwise, but again, I'm going to flip my rules, so that makes this R. Cool? All right, now just to be an extra big pain in the ass, go ahead and name that compound for me.
I got 3R4S, 2-fluoro, 3-pentanol.
What fluoro?
2-fluoro.
Yeah, so then it wouldn't be.
I got 4 fluoro.
So it's 2S, 3R.
Oh, right. Yeah, I got that backward. My bad.
Yeah. 2-fluoro, 3-pentanol. All right, we got one more example to do, and that is using the Fischer projection. Which, if there was any good to come out of the sugars, maybe it was reminding us all that Fischer projections exist. All right, my goal for this one was not only to remind us about Fischer projections, but to make it a huge pain in the butt to assign priorities as well. Okay, because these are all kind of similar groups here. What is this right here? COH.
That's an aldehyde, right?
Aldehyde.
Yeah, awesome. All right, so that is that guy there, and then COOH is
Carboxylic acid.
carboxylic acid. Awesome. All right, and then this guy over here is just an alcohol group. What is the highest priority of these three?
The carboxylic.
The carboxylic, followed by
Aldehyde.
the aldehyde, followed by the alcohol, right? Just increasing number of oxygen bonds, carbon-oxygen bonds. And remember, if it's double bonded, as is the case with both my carboxylic and my aldehyde, then I count it as bonded to 2 oxygens. All right, and then in the Fischer projection, these are 1 to 2 to 3. These are clockwise. If it's a Fischer projection and the lowest priority group is horizontal, what is that going to make this?
Clockwise.
1, 2, 3.
Clockwise
would-
corresponds to R or S?
S,
R.
right?
It's S, yeah. So the rules for Fischer are going to be the same as these down here. So this is also Fischer with lowest at horizontal, which is like the standard way of drawing your Fischer structures, is to put that lowest priority group in that horizontal position. If it were to be in the vertical position for whatever reason, then it's back to our normal R clockwise, S counterclockwise. But again, convention is going to have it, 9 times out of 10, you're going to see it in that horizontal position. All right, and then the rules are flipped. So clockwise would be S, counterclockwise is R. Cool? Crash course back on stereochemistry. Okay. Okay. So little acid and base practice all the way back to chapter 2. Rank. All these in terms of increasing pKa. I'll make it even more obvious. So these are 2 separate problems. Okay, so first of all, highest pKa versus lowest pKa. What does that mean in terms of like how good of an acid it is? Best acid is going to have the highest or lowest.
The lowest pKa.
Right, so your better acid is going to have the lowest pKa. Worse acid is going to have a high pKa. What is it that makes a good acid a good acid?
A really crappy base.
A really crappy base. Awesome, right? So that is sort of our logic here is we're going to look at these conjugate bases and ask ourselves which one is the crappiest at being a base, i.e. which one is the most stable, is happy all by itself, right? So which one of these is the most stable?
Fluorine.
Fluorine, right? So this fluoride ion is super duper stable. That makes it a crappy base, which is what makes this the best acid. All right, and then if we're going to go to the other extreme, which one of these is the best base?
Would be that carbon ion?
Yeah, absolutely, right? So this guy here is the least stable. It's the least happy to be just sitting there as an ion. So it's the best base, and in contrast, that means that this is the worst, right? Let me actually do this one. Oh, I lied. All right, so this is how they would sort of rank from lowest pKa to highest pKa. And what would sort of be the logic behind why is this fluoride ion so much more stable than this carbon ion?
Electronegativity.
Electronegativity, absolutely, right? Fluorine is just more electronegative, more willing to hold that negative charge on it. Awesome. Okay.
Does that apply to the hydroxide and the amine as well then? Because isn't hydroxide like a super strong base, therefore its conjugate acid water would be, well, I don't know.
Well, so so if we're going to use this same electronegativity argument, right, to be like it's more stable as an ion, what's more electronegative, oxygen or nitrogen?
The oxygen.
So this guy is indeed more stable. It is still a good base. I mean, it's still what we would consider to be a good base. It's honestly, it's the most common one that we use. But this amide ion is an even better base, right? So yeah, so in terms of lowest pKa, so this is good acid, bad acid, and the conjugate bases trend the exact opposite. So this is a good base, and this is a bad base. So your instincts of thinking a hydroxide ion is a good base is true, all right? But in comparison to the amide, and certainly in comparison to the carbon ion, it's not even close. And then what about when we're going to compare all these halogens right here? What's the order there? Which one's the best acid?
EHF.
Which
I
one?
thought it would be the HI.
It is the HI.
Okay, that's what I thought.
Yeah, so this is the best, followed by the bromide, followed by hydrochloric or hydrobromic, hydrochloric, hydrofluoric. All right, and it's the exact same as before in terms of if we look at the stability of these ions, but now it's not going to be an electronegativity argument, right? So that we said it works when they're all in the same row. When you're talking about the difference between an iodide and a fluoride ion, what's the biggest difference between those two?
The size.
Their size.
Size, absolutely, right? This dude is huge, and this guy is super tiny. So when you are a larger ion, they are more able to support those charges because they're what's called more polarized. If you guys remember, I kind of told you to think of when things get bigger, you think of them as being kind of like squishier, all right? It's basically—
They're soft ions.
They're softer ions. It's able to hold that negative charge because it's so much further away from the nucleus. So this is this argument, whereas of here we use this argument of electronegativity. Here it's polarizability. But yeah, hydroiodic acid is like the strongest acid that exists. All right, and then we go down here. If we're going to rank these, which one is going to be the lowest pKa?
Phenol.
It's not so phenol is a decent acid, but
It's the benzoic.
the benzoic acid
Yeah.
is still better. Right, but phenol is certainly a way better acid than cyclopentanol. And why is that? These all have a sort of similar argument here.
Well, the
Again-
other two have like aromatic capabilities.
Yeah, so this is now
Stabilize
going
it.
to be a resonance argument, right? So a carboxylic acid, that OH group is way more acidic than a normal alcohol group because it's stabilized by that other oxygen through resonance. Similarly here, this phenolate ion is much more stable than this alkoxide ion because that negative charge is stabilized through resonance. Okay. So crash course in acid bases. And then, so remember, if then I take an acid and a base, and I ask myself which side does this equilibrium lie on? Is it going to favor products or reactants?
It'll favor the product.
Yeah, right. So this is a good acid. This is a bad acid, or relatively speaking, right, if I'm comparing pKa's. And these equilibriums always lie in favor of creating that bad acid. All right, another way to think about it is the better acid is going to win at giving up its proton. Cool. All right. Crash course through acid-base stuff. Where are we at? Ooh. All right. Let's do some alkene and alkyne reactions. All right, you guys help fill in this wheel here. Okay. Let's start here. First of all, what type of reaction would that be?
Reduction.
Yeah, and so what is our sort of go-to reduction mechanism or go-to reduction tools?
Palladium.
Yeah, so this will be hydrogen gas and then your palladium carbon catalyst. What about this guy here? This is like the very first reaction mechanism we ever did in this course.
I used HBr.
Yeah, right. So remember, almost all of our reactions with alkenes were under acidic conditions because that acid will create a carbocation. In this particular case, which one of these carbons, carbon 1 or carbon 2, is going to be the most stable carbocation?
Carbon 2.
Carbon 2, right? So primary is going to be the weakest. Secondary, tertiary will be the best. It can also be supported by resonance, right? So if it's right next to a network of pi bonds, that's also good. But that's our sort of increasing. Remember, exact same trend for radicals as well. We'll do some radical review next class, but those two should kind of be filed away in the same category in your brain. Yep, so that's how we get bromination on that most highly substituted carbon. Let's do this guy next. What's the easiest way to put an alcohol group on there?
I used water and an acid catalyst.
Yeah, so that'd be H2O as well as our strong acid. I want to remind everybody that we actually did have a second way of doing this as well, using mercury, this like mercury acetate compound, and then followed by any sort of a reducing agent, but yeah. All right, but this would also put an alcohol group on that most highly substituted carbon. We'll jump to the least highly substituted, the other one here in a second, but let's go now to this one because it's very similarly related. If I took this and I had an acid catalyst, but instead had some sort of an alcohol, that would behave in the same way, right? So these two can kind of sit in that same group in your mind. If you use water, it'll attach an alcohol. If you use water, it'll attach an alcohol group. If you use an alcohol, it would create, what do we call these guys?
An ether.
Ethers. Awesome. All right, and then lastly, how the heck do we get substitution on that least highly substituted carbon?
Was it the boro one?
Hydrobromination.
Yeah, I couldn't remember what it was though.
BH3. That should be the number one thing that jumps out. Like if we wanted to complete it, it's in THF followed by OH minus H2O2, H2O. The nice thing about these multiple choice tests, you can sort of just key in on that one key thing here, right? And that should be this HB3. Okay, now let's move to some alkyne reactions. This D is just like, it's a hydrogen, but it's a deuterium, so we can keep track of where it moves when we do these two reactions over here. But how do we get carbonyl groups?
You have to reduce them somehow, right?
Yeah, it's a good guess, yep. Right, so these are all going to be, remember, the alkenes and the alkynes all underwent these addition type reactions, okay? What would happen if I took my alkyne and I did H2SO4 and H2O? What would I expect, just like up top?
You'll get an alkene.
You get an alcohol.
An alkene and an alcohol, so let's just draw this out real quick. That means that there's a double bond there and an OH group there. What do we call this guy?
Enol.
Yes, right? And what do enols do?
Tautomerize.
They tautomerize, right? So this is how we would get, actually this is I went the wrong direction. This is how we would get to here, right? And you don't have to do anything special. So basically you just create your enol and that will tautomerize to these carbonyl groups. And then if I wanted it on that less highly substituted carbon, then I would just have to use my strategy that I used up here of putting an alcohol group on the less highly substituted carbon, right? So this is then going to use that BH3. I'm just gonna put ... for now, right? But that's how I would get to RC, which would take me there. Right, so remember our strategies of putting alcohol groups on our alkenes. That was how we put carbonyl groups on our alkynes. All right, and I guess first, if I wanted to reduce this sort of all the way, that's when I would use my H2 and my palladium catalyst. If I wanted to stop at this alkene step, there were two different ways to do it, and the difference being the stereochemistry. How do I get my syn addition? First of all, what the heck is a syn addition? Am I talking about the top one or the bottom one?
Bottom one.
Yeah, right. So being added to the same side, there are these two hydrogens going to be added to the same side.
Was it
What was the dude's name?
Lindner?
Yeah, this was Lindler. And Lindler is just a type of palladium carbon catalyst that's been kind of made to be not so great. The other one, does anybody remember what I would do?
Like
Is that-
Na
That's,
or lithium
It's
and NH3?
Yeah. So the real deal is the sodium or lithium, right? So you need solid sodium or solid lithium. That's like kind of the real player. And then this takes place in cold ammonia. All right, but that's how we can get our two different stereo products. Okay, alkene, alkyne, what else can we do? It's just, we're getting a little busy here. This is gonna be sort of a multi-step synthesis kind of deal. How do I convert an alkene to an alkyne? I'll give you a hint. You got to go through one step where the last step is going to be an elimination step. All right, so let's just think real quick. What happens if I treat this with, I really want it to be, I don't know how to spell that, elimination product, right? I don't want any substitution product, so I'm going to use this big bulky base. What would that give me?
Wouldn't that give you the same thing?
Yeah, and actually, this is maybe not the best example. Let's cut this off real quick. All right, so yeah, this would give me, and actually I would get kind of a mixture of that and that. So that's why I want to simplify things. Right, but my point is that we have another thing that we can add on there that can be easily eliminated, and that is if we take our alkene and combine with Br2. What do we get?
Well, the Br2, wasn't that an anti-Markov addition?
No, it was an anti-addition. You're like half right. So it's not that it's anti-Markov, right? That would mean that it goes on the less highly substituted carbon. You're going to get it on both carbons, But you're now thinking one step further, which is the stereochemical implications, which is they get added from opposite sides. So in this case, if we have Br2, we get a dibromo product that then we can then toss in some tert butoxide in, eliminate both of those bromines off, and that's how we get an alkyne. All right, last little bit. All right, so I'm going to take both of these and add in that tert butoxide. All right, so I can favor the elimination product. Tell me whether these are going to be E1 or E2 and draw out that mechanism for me. All right, so first of all, E1, E2, what the heck am I talking about there?
How many steps it takes, right?
Yeah, so yeah, the question is does this happen in one step where we have the elimination, you know, the leaving group getting kicked off at the same time as our alkene is forming, or does it happen in 2 steps, right? The 1 and the 2, though, aren't the number of steps. The 1 and the 2 are the number of reactants that are involved in the rate limiting step. So this E1 is the 2-step process, E2 is 1 step. All right, so kind of easy to get mixed up, so make sure to have that in your mind. It's how many reactants are involved in that first step, right? So in an E1, the first step is the formation of that carbocation. There's only one molecule, one molecule that's involved in that, right? Whereas in E2, it's the base and your molecule that's being eliminated that are in that first step. So first of all, this tertiary alkyl halide, is that going to be E1 or E2?
E1.
Yes, that's going to be E1. So the first step here, come on. So E1, that means that the first step is just that formation of the carbocation. Base isn't involved at all yet. So this. Then we get a tertiary carbocation. Then the next step is the base coming along, removing that hydrogen, and at the same time, that pair of electrons comes down to give me my double bond. All right, so again, E1, because in this first step here, we only have 1 species. Is my product E or Z?
Would it have that configuration?
Yeah, so that was a trick question.
Yeah.
It doesn't have any sort of stereochemistry because these 2 groups are the same. Okay, and then we get a primary alkyl halide. This is going to be E1 or E2.
E2?
Yeah, so this is the E2. And again, that's because we're going to see that 2 species are involved in this first step. All right, so if I draw an E2 mechanism, that means that my base grabs the hydrogen, this bond forms, and this guy gets kicked off all in one shot. But again, it's E2 because we got 2 species involved in that first step. Really the only step. All right, so that's going to do it for today's sort of review of first semester stuff. I know this is a bit of a crash course and stuff that we haven't thought about in a while. Nonetheless, again, like you guys would be surprised how sort of good you've gotten here. Let's just look at this first reaction here. What's my nucleophile?
Butoxy.
Butoxide, right? What's my leaving group?
Bromine.
The bromine, right? So things like that have become sort of second nature to us, but we're technically first chapter stuff. One more thing that I want to say with regard to this sugar business. The homework for this chapter, for chapter 20 that I had posted, I'll make it optional. If you do it, you'll get the 10 points. If not, it won't count against you. Same thing with that take-home exam. I want to hold true to that promise of like there's sort of a take-home kind of thing that you can do for points on this. If you guys do it, great. It'll help your grade. If you don't do it, it won't harm your grade, okay? If you feel like you need to focus on studying for final exam stuff, go for it. If you could use the extra points, do the take-home exam. All right, at least take a look. It's posted on Canvas already. It's under the study guides section. And there are just a few, you know, a bunch of questions that pertain to sugars, that pertain to all that material that we learned last week. Frankly, if you are comfortable with your grade, you can dump it and, you know, focus on final exam type of material. Okay. With regard to last semester, I will just tell you straight up, we're not going to have NMR or IR stuff on the exam. All right, we'll have one practice problem with NMR stuff, but there's not going to be NMR material on the exam. Okay. But yeah, that like, you know, hint, hint, nudge, nudge, all the review we did today, right? So being able to identify hybridizations, acid-base sort of stuff, the reactions of alkenes and alkynes, not a bad idea to look over that alcohols chapter again. But yeah, those are sort of the topics to cover. Really what I would like you to do is, if you found yourself lost at any point in today's lecture, find the chapter and the lectures that pertain to that. I posted all the old lectures from last semester on Canvas, so you guys shouldn't have any problem finding that. Yeah.
I was actually surprised at how much I remembered.
Yeah, I mean, we've recycled a lot of the stuff over and over and over again. So it is a lot of like, it's not like last semester and this semester were disconnected at all. They fit into each other quite nicely. So I agree. I was like, I got that question bank, and the one from last semester was larger than the one from this semester. And I was like, oh crap, how am I going to make this exam? And then I looked at them, and I was like, these are going to be easy for them. So not saying that there aren't some hard ones in there, but for the most part, you guys have like buffed up your skills to the point where last semester stuff is a cakewalk now. Okay. You know, as always, if you're studying, you have problems, let me know, email me, we can hop on Zoom, do some problems, blah, blah, blah. If you are, you know, one piece of advice for trying to pinpoint what you don't know, right? I mean, that's the hard part, is we've learned a lot of stuff. You don't want to try to review every little single thing. You want to figure out where your holes in your knowledge are. Go back and look at your past exams. Where did you lose points, right? That's a great indication of something that you didn't know and need to spend more time on. Don't sit there and practice nomenclature that you know for 4 hours. That's not going to do any help for you. It's easy and it's fun and satisfying in that way, but we need to direct time to what we don't know, right? Not like sit there and play with stuff that we do. So yeah, see where you lost points. Yeah, it's my advice. Cool. All right. Just if you are going to do the take-home exam, it's due in a week. All right. So next Tuesday is when it would be due.
How much is that one worth?
So it's going to be 50 points. So it's like a third of a normal exam.
And then you submit it onto Canvas just the same way as the other tests?
Yeah, so there's an assignments tab. Actually, if you click in the assignments, it will take you to the actual PDF of the exam as well. All right, and you can do that like you do your normal exams, or you can print it out and fill it in. I don't really care. And the intention is open notes, right? So there will be sugar names on there. You just look through your notes as to what that sugar is, etc. Cool. All right. All right, y'all. Well, have a good day. And yes, I will see you on Thursday for more review. Yay.